Now we're going to be talking about, like we said, the different cases when we do a direct proof. And so we want to think about, if we represent a number mod 2, what could happen? All right, well, if I divide 2 into any number, then I know my remainder is either going to be a 0 or a 1, right? So what that means is that when I'm trying to represent the integers mod 2, I could write this as 2 times q plus 0, or 2 times q plus 1. And of course you could just say 2q and 2q plus 1. So that's a way to represent numbers when you're doing things mod 2. And we've seen that before in the previous section, that when you talk about even and odd, you can write it in one of these ways. In fact, it was in the definition itself. But similarly, we can do this when we're doing things, let's say, mod 3. All right, it could be that when I divide something by 3, that I get, it goes evenly, so a remainder of 0. I could get a remainder of 1, or I could get a remainder of 2. And so what that tells me is that when I'm doing things mod 3, I could have any of these scenarios. All right, and of course you can just write this one as 3q. All right, so up here, that's the way you would represent it. Down here, these are 3 ways that you could represent something when you're doing something mod 3. And as you might can guess now, if you're doing something mod 4, you could have a remainder of 0, so just 4q plus 0, or just 4q. You could have a remainder of 1. You could have a remainder of 2, or you could have a remainder of 3. But you will not have anything bigger, because then that would mean that you could have divided it again and had a bigger quotient. All right, so those are the 4 ways to write that. And then if you're talking about something mod 5, you could write it as 5q, 5q plus 1, 5q plus 2, 5q plus 3, or 5q plus 4. All right, and those are your only options. You can't have anything bigger than 4. You can't have anything smaller than a remainder of 0. All right, now this is going to be important, because when we talk about proving things and breaking things into cases, it may be that we need to do things, mod 2 or mod 3. And really what we're doing is we're just applying the quotient remainder theorem. All right, so that's probably the way we would word that. And of course, the smaller the number is, the less cases you have. So if you're doing something and you want to represent it mod 2, you only have 2 cases. If you had to go to mod 5, okay, well now you've got 5 cases to consider. So, try to go with something smaller, but sometimes it just won't work, and you have to go to a larger number. So our first theorem we want to prove is 3.4.2, and it says any 2 consecutive integers have opposite parity. And so when we're looking at our 2 consecutive integers, if we call, one of those x, then the other would be x plus 1. All right, and we want to show that x and x plus 1 have opposite parity. And opposite parity would mean that if one is even, the other is odd. Well, there's our 2 cases. All right, so in this situation, let's just say we use x and x plus 1. Our 2 cases will be, number 1, x is even, and our second case could be that x is odd. So if we want to write this in an if-then format, here's a suggestion. All right, if x is an integer, then x and x plus 1 will have opposite parity. So notice here that I'm sort of forcing the consecutive integer part. We know if x is an integer, if you add 1 to it, you get an integer. So really in our assumption, we have that both of those are integers. But then we want to prove that the original number and one more than that have opposite parity. All right, so if we want to start our proof here, we've already said that we're going to have 2 cases on the previous page. All right, it could be that x is even, or it could be that x is odd. All right, so let's say we start off by saying, let's let x be an integer, okay, or assume, if you want to use that word. All right, and let's just say we will have 2 cases. first one is x is, let's say, even. It won't matter which case you do first, as long as you do both of them. All right, so if we say x is even, we can say then, by definition of even, there exists a k that's an integer such that x is equal to 2k. So then if we want to consider x plus 1, that would just be 2k plus 1. All right, now by the definition of even, we know that x was equal to 2k, and then if you just add 1 to that, you get 2k plus 1, and this is just very natural because 2k plus 1 is an odd number, and that's actually the exact definition. All right, and so by definition of odd, x plus 1 is odd. And we've already said that our k is an integer, so if you wanted to repeat that, you could, because normally when you're doing this, you would have to say something about this thing that you're multiplying times 2 and adding 1 to is an integer, but we've already stated that. And so by definition of odd, x plus 1 is odd. And so therefore they have opposite parity. So when x is even, x plus 1 is odd. All right, so that was one case. All right, the next case is x is odd. And so then, by definition of odd, there exists a k. Now you might wonder, can we use the same k? You're okay because the cases don't overlap, so this is either case 1 is true or case 2 is true, so you're okay to use the same k. If you're not sure, it would be better just to use a different k. So, if you wanted to call this up here case of 1s, then you could call this case of 2. So I'd rather you err on the side of having too many different integers than to not have enough. All right, so there exists a case of 2 that's an element of the set of integers such that x is equal to 2 times case of 2 plus 1. So that's what the odd tells us. And then we'll just basically repeat the process that we did in the first case. So we'll say now x plus 1 is equal to 2 case of 2 plus 1 plus 1, which implies that x plus 1 is equal to 2 times case of 2 plus 2. All right, now this is not the exact definition of even, so I can't just say by definition of even, but I can try to make it fit the definition of even. If I just factor out a 2 here, I'll have 2 and then in parentheses case of 2 plus 1. All right, now it's not given to us that case of 2 plus 1 is an integer already, so we need to make that argument. So why is what's inside of here an integer? Well, by the closure property. All right, but we need to state that because it's not already stated. All right, so we'll say by the closure property, if you want to write out what it is, the closure property of integers under addition, by the closure property, case of 2 plus 1 is also an integer. And so now x plus 1 fits the exact definition of an even number. And so we can just simply say, by definition of even, x plus 1 is even. All right, so let's see if we're done. All right, so let's look at the first case. First case, we assumed that x was even, and we showed that the next integer, x plus 1, was odd. All right, so that takes care of the case where the first number is even. The next case says, okay, well, what if x is odd? And we actually just showed that the next consecutive integer is even. And so even and odd, those are opposite parity. And so we're basically done, except for just to write our final conclusion, which is always a good thing to do. All right, and so we'll say, therefore, x and x plus 1 have opposite parity. Now, one thing you'll want to make sure of is that you have indeed covered all the cases, if cases are necessary. In this particular case, x is either even or odd, so that was definitely all the cases that we had to consider. Another thing you want to think about is, once you break it into the cases that you have, are those the two cases, or is there something else that would be more helpful? All right, in this particular one, it was pretty easy to go through and do the proof, but we'll see one in just a few minutes where we have to consider something different.